afternoon. So today we're going to have our first lecture on finite element. Okay, so this is the lecture on this subject. Okay, this one is a graduate course, mastery for solid mechanics group. That is open to other disciplines and also finance students. So this subject has been selected as the strength analysis professional subject. The undergraduate program we want to implement. 因为这门课也适用于这个大专所以基课程学程。Okay, what are we going to study from the finite element? Okay, so we are basically using a systematic method to do structure analysis. 所以我们有些人的课你可以想象成是结构分析 ，OK， 动力分析 ，OK， 但是它是一个很系统化的分析方式，做的是最简单的模拟。然后，但是用了很多元素去把这个物件，然后去做这个比较形状的分析。So the target here is actually you are analyzing a spring. Okay, let me draw something. Okay, later I will show you. So you are analyzing a spring. Okay, and you are analyzing a beam, and you are analyzing a solid. Okay, all by discretization. So there will be translation from structure element to finite element. So in this course, we're going to refer to this textbook. Okay, you can also refer to the lecture notes. Okay, to help you do the analysis. Okay. So the topic to cover in the coming series include first this week we are talking about stiffness, and then we're going to talk about thrust equation, equation, equation. Then we're going to analyze 2D element, then triangular field. Okay. So do the dotted by this jargon, okay, it will become very natural after you learn to do that job. Okay. So in this subject, you got to do your homework. So you carry 20% of your final score. Okay. Besides that, you are asked to do the analysis and got to submit the report for the hands-on. And finally, you will be grouped to do a project, okay, by group, okay, before you got your intern and final examination. 所以这个就是除了你们平常做作业、做 analysis 的这个操作。做它的最后的有一个project， 后面其他分数就是Okay, this is the contact information from me and also the teaching assistant. The teaching assistant will be Jing Yi and Yan Guo. Okay. This is the brief introduction about the course. Then next we'll come to the core of the我们今天基本上学的都很简单 ，OK， 形象上很简单，我们就只学弹簧 ，OK， 所以这个弹簧是打锤子、打楔的 ，OK， 都是一样的 ，OK。不过后面你们会看到，我在写公式的时候，要去弹簧，你们基本上用那种公式。So what do you need to, what kind of formula you need to use? Okay, so you need to describe the spring deformation. 所以特定横的部分，这个垂直的不可定律怎么去？不可定律是什么？ final name will be L plus X. Okay, so this is the extension. The more you put, the more is the extension. Okay. 现在我们来问一下这个同学，水平的弹簧跟垂直的弹簧的定律一样，一样。Is it going to be the same for the root saw? Okay, this is F equal to Ax. Okay. How about the spring horizontal? Is it going to be the same? 水平的弹簧点就是这个为所以现在就来，对，5个定律是告诉你材料外力是一样的，水平的弹簧跟垂直的弹簧是用同样的定律。那有觉得一样的同学，那举个手，一样的来举举手。那我们问一下一样。OK 好，对 OK， 那的确看到没有 ？OK， 你们学的5个定律，这个有点学。对，你学的是应该是。这是外力 ，so this is the external force that you are studying. Okay, this is the external force. Okay, and then this one, F here is also external. Okay, so it just happened because it's a line. So your internal force is going to, if you do the cut here, so on this subject, you're going to have a spring force. On the spring alone, you're going to have the reaction, it's a spring force. 所以严格意义来讲，你这5个定律怎么写？你把它写成了外力，刚好等于你的内应力。然后这个 x 呢，是因为你内应力造成的变形。所以左手边这边，其实我不大关心你的外力是中医还是其他方式产生的，你只要是力 ，OK， 反正在接触点，如果这是接触点，这是外力会被内力去抵消。然后作用在弹簧上的这个力呢，就是反作用力。So when you are doing this, divide and conquer, then you can see that what the spring is subjected to. Okay, including what? This is your reaction. But this reaction is equal to the spring force. Okay? 差吗？是吧？所以5个定律，你觉得应该是一样还是不一样？一样。好，谢谢。OK， 当然这个因为弹很重，如果弹很自重，垂直的话，它有叫做自重。OK， 但是不管是不是自重，对于弹簧而言，简单弹簧，它只是产生末端作用。OK， 末端的弹，上弹一下，它方向要向。所以这门课有一个很大的重点，你这门课有不同于你一般做有些东西，有些东西到最终是用软件，但是很多人用软件用到 LE、LR，OK， 那你如果本身的假设就错 ，OK， 你对 B 没有感觉 ，OK， 那你做的所有分析。就很不错，而且有些元素分析的最基本原则是什么？简化，简化的模型测一下，具体复杂的模型测一下。它如果结果是同一个量子，那有可能你分析的是对的 ，OK。所以有些元素它不是一个reality， OK， 它只是一个经验值。给你测到，它很可能是你编辑的错误。Okay, so what else we going to model? Okay, another example that we are going to model today is a handbag. Okay, so let's see. Right now, okay. OK， 我们来分析最简单的有限元素的东西。OK， 那你一个弹簧 ，OK，this is going to be one element of the spring. Very simple. You apply force. Okay, then you got your elongation. Okay, this is a simple spring. Okay, next. What happens if you have two springs? Okay, you can have two springs supporting a mass. Okay, so you see this is also not too difficult to analyze. Okay, so you recall what's the push force? F equal to kx. Your x is equal to the force divided by k. Okay, correct. Okay, second, how do you analyze this? Okay, if they undergo the same deformation, okay, you can simply define your total spring force. Okay, it's going to oppose the weight. Okay, then you can write. Okay, this is your force summation. If you make the x positive downward, then you can write the force is going to be opposed by 2 times kx. Okay, the spring force is x here, x spring force is x here. Okay, so you now do the rewriting. Okay, force sum equal to 0, then you're going to have, if this force sum equal to 0, this is the static, plus your mass and acceleration to 0. Okay, so then what did you write? You write 2kx equal to mg, and then x equal to mg equal to k. 我觉得因为一点印象开始有点上手，对不对？大家这让大家觉得，哎，我当年读的这个经济学没忘记的时候，那我给你出一题，那你怎么分析你的表的对宝啊 ？OK， 这题也不难到。OK， next the same question. you now have the sling back. Okay, let's say the spring, the sling back. Also has the weight of mg. Okay, it's pointing downward. And then it happens that, oh, my spring back, my sling back has the sling, which is elastic. If this is elastic, so it must have K delta L. L for what? L for the length, half length. Okay? So how would you find out the extension? Can you find out the extension of your sling? Okay? In this case. Okay? So I think it's not difficult to analyze this. Okay? Force. Okay? Because you see that I'm going to have half the force here on the left, half the force on the right. And then if this is the angle theta, okay, then I can find out how much is the tension. How much is the tension? The tension must be equal to, okay, let's see what should it be. The tension times cosine theta is equal to F over 2. Okay? So how much is the tension? The tension is going to be the F over 2 divided by cosine theta. And then next, how do you find the extension? Okay? How to find the extension? Extension is very clear. It is equal to the tension divided by the K value. And then next, the toughest part now. I would like to know how much is the sinking down of the bag under the bag. 所以说那个一根弹簧的5个定律，2根弹簧的5个定律，你都可以解决。那现在斜的弹簧的5个定律，还是一样的5个定律。斜的弹簧的5个定律是一样的5个定律。OK， 没有变，对不对？所以同学当然。我看到你 ，OK， 躺着看，立着看，还是没变。那问题就是你的动作，OK， 相对这个参照点，比如说水线，比如垂直线，却因为你的姿态而可能有改变。所以这个 OK， 是这两个部分，让我们可以参考。好。这是一个开场白。如果今天的课你会读不懂，那你们可能就复习一下我们的材料例句。So you cannot grasp what is taught today. So you got to go back and revise the mechanics. Okay. Of material, of statics. Okay. So what we analyze really is we're going to later show you. We are not going to do hand calculation anymore. Okay, we're going to do a systematic approach. Okay, because finite element method is the method to teach computer how to calculate the structural deformation. Every procedure must be standard. Okay, so that's why the dummy computer can do calculation. It has high computation power, but what it does is something dummy. Okay. 所以你知道有些元素很深，你们读的材料比有些元素难很多。那为什么有些元素这么深？它是不断的切割，把一个复杂的形变切割到很小的元素。那很小的元素的形变就可以用一个很简单的5个定律去模拟。其实它的精度超差的，它只是说用算力去取代精度。 同样的 ，OK， 在 AI 这个时代，不要害怕被 AI 取代，你只要用很低的算力去做对的事，那 AI 呢，它要用很大的算力，OK， 它不见得算对。So what you see here are simple spring. You know that the idealization of the spring. 看到刚才的排行榜 ，OK， 你可以看看这5颜6色的排行榜有多少彩球，一圈一圈 ，OK。但实际上它被模拟出来就是简单的一个 F 除以x。为什么还要搞出这个具象的排行榜？你想想看，这个排行榜。它是走向延伸，它也可以扭转 ，OK， 你甚至还可以让它做这个垂直方向的一个跳动 ，OK， 所以实际上有些元素取决于你的元素的选择，它只模拟你局部的这个形变，就比如轴向形变，就是我们画在那个这样讲。那横向它有转动，我们后面也可以用做到这个去打对吧？所以 today analysis you're going to see that you're going to analyze complexity, but all this complexity can be discretized into small elements and analyzed into single thing. So this is a triangular tetrahedral solid, and this one is a cuboid. So how to do the discretization? This is the solid, okay, in reality. But in the analysis, are you going to analyze it as solid, or are you going to analyze it as a shell? Okay, it all depends on the accuracy you want to see. 这张纸是有厚度的，比如说0.1的，你要把它模拟成这个立体。但你需要很多元素，因为每个立体元素起码有1、2、3、4 ，OK， 那8个，1、2、3、4，8个节点，每个节点3个质一 ，OK， 那你如果想简化 ，you going to reduce the complexity, then you know this became like a shell, okay? Then you use the right equation, then you can use to replace the solid element into a shell element with 4 nodes. But in these 4 nodes, are you going to save up the combination? Not necessary. Because for the shell, okay, you might have, what do you have? You have the deep diffraction, okay, in the longitudinal direction, and also in the v direction, and also you have vertical deformation. 所以你简化的是什么？每个自由度你还是有位移，刚才的位移是向前、向左、向上的位移 ，OK？ 那你把它换成这个2单元或者是翘单元，那每个节点上面就只有上下 ，OK 上，然后向前、向上，还是3个位置数。是变成了2个元素，一个移的位置数 ，OK， 然后那一样，但是你是把节点数减少从8个变成10个 ，OK。So this is a bit of a history about the evolution of finite element. Why do I have to go through this? Okay, it's the same way that we learn structure analysis. Some structure, solve it by hand. Later, want to consider solid, then you have to do continuum mechanics, okay? And if you don't want to do too much hand calculation, then you do discretization, then you in the end have finite element. 所以你们上机械的课，跟这个有些的联化非常接近。大1还是大2读的经济学，就是结构分析。那你后面材料力学，有深一点，应变场，这个是还是说你要大数1要读连续题。 的人是数学家，他会解决很多事。OK， 他的做法是，他是把这个位置当成场，所以你的所有的力当成场，可以说用 H 类似，但是这个场不仅仅是位置，所以你的非常 analysis。So you are not just trying to analyze the displacement field. You can do analysis of the temperature field. You can do the analysis of the flow field in terms of velocity, or you can analyze electrostatic field. Okay. So all this is the abstraction of finite element vector. So 一开始，同学为什么这个机械是工程之母呢？图片的要来机械掰一下，知道吗？机械是工程之母，有点知识。出去遇到电，你解决不了的问题，但凡你要至少还是实际上摸得上，要来掰一下这个机械组装。机械是工程之母。留下。后座椅在刷手机的同学，机械不能控制住。依照电机，你要跟他说服机械成这个的。派你出去，一定要会。电机的鼓掌 ，OK， 那你开个电动车，So how do you use the electromagnetic field? Okay, even though you know that it is electrostatic or electromagnetic field induction, but the way you calculate how much energy stored in the motor must be the output of the electric motor is in terms of torque, in terms of speed. These are all the measurement in mechanical parameter. OK， 所以不说别的，你要证明机械是工程之母，可以去看看所有度量的 ，OK， 都最终会变成牛顿米时间 ，OK， 包括电压，电压，同学。下次遇到这个电机的同学去骗他一下，电压的单位是什么？画一个，电池的电压是什么？电压单位是什么？伏瓦，对不对？那现在你要去骗电机的同学，把电压写成机械的，要多写。电压的正解叫用机械的形式来写，电压叫什么？如果这个是电，这个是，那如果是之间的电子在对。它有移动 ，OK， 力就是你的一个电呢感受到的那个电场，电压的单位叫 OK， 每颗电 OK， 这个单位是牛米。为什么要教你们这些？给你大概知道这个有限元素广阔的发展，它基本上就是一个功能原理，后面会有一些变化，只是常的变化。OK， 这个会考，就是 下。Okay, so let's come back. When did you have to do structural analysis? Okay, it happened because of the needs. The needs come from the requirement to analyze fragile structure. What are the fragile structure that need your deformation analysis? Aircraft is the one. Aircraft is the one which is called fragile. Why? It is not as strong as a building. Why an aircraft or spacecraft cannot be as strong as a building? You want it to fly. You never expect anything to fly, isn't it? Okay? So the structure must be very lightweight and the area must be very big in such a way that you gain enough lift force from the airflow, but you have structural integrity to sustain you in the air. Okay? So the first structural analysis was done by a Boeing engineer or Washington University professor Croft. OK， 所以你们今天上的课，不好意思，这么多年了，多少？那什么时候写的？1956年写的，基本上就是你们现在课的东西，也不会多。OK， 因为你们手算的知道这个线，因为他当年的确是用手算，他要用电脑算，他就要用当年的超级电脑。OK， 那时候超级电脑很大。Okay, and then the first textbook on Thailand was published by Minty. He is the guy, he's a mathematician, he's not a structural engineer, but he theorized. Use the matrix analysis to analyze solid. Okay? Banner solid. Okay? So this is a practice. And what's the first finite element software? It's the one coming from NASA. Okay? NASA structural analysis software is called NASSTRUCT. Okay? So it was released in 1968. Okay, so I'll play the video so that you can see the cost relationship of this structural analysis. Okay, let us see. Look at the所以你可以看一下当年分析飞机，这个有限元素的网格分了多处。So you can see that how rough the discretization of the aircraft structure in the early days. Does it work? So 有些元素需要把网格打得很细吗？不需要，你只要够用就好。最重要的是你测出来的结果可以让工程师设计出安全可靠的。所以现在的 AI 没有必要，你如果能手算，那不用 AI。但是这个有些人可以讲是，有没有听过 digital twin？OK， 有没有听过？做 AI 的，那 simulation to reality， 这个就是当年的 digital twin， 1951年就 OK， 这是现在换了一个说法，但是我们也知道。这个东西这么久都有，但是它的这个准确度建立在工程师的这个理解跟假设。你如果假设说错误，那的确对你只是一个灾难。好，我们看一下当年的有限元素，主要就是为了针对这个飞机这个。高速飞行的时候，震动。So this example that the structural analysis is going to be useful. We will analyze what's the resonance frequency of the structure. weight. So it's an interaction between the structure and the external loading. 所以你如果坐这种飞机，自己要快快，这个不要乱掉。大概做一个分析。那对于元素的需求 ，next we're going to analyze what kind of element is necessary for structure analysis. Okay, of course, you can see that the strongest and most primitive structure are the rock. Okay, they are block that you can tie them up. And then next, since the invention of the steel structure. Okay, you have Eiffel Tower built out of the steel structure. And next, see this Eiffel Tower is quite heavy. Okay, you can't span them across the bridge. Okay, in the end, you need to use the cable. Okay, 所以你从有限元素分析法的这个角度，这个是一个体元素，这个是量。后面你的这个吊桥的这些钢丝，那就是变成了你的感元素。So in the end, you have to know what is it for. Is it the 1D rock or cross element, or is it the beam element? Are you going to analyze it using a shell, which is the plate area element, and finally you will go out solid, which will be quite important. So in this case, you going to do analysis. 在三只小猪的故事，那我们来讲一下这个三种元素。来，我们快速来问一下同学，来，后座同学，砖屋是什么元素？线、面、底元素。OK。我们就沿着这条线，来 A 同学，来 A 同这个来戴眼镜，这个这个用木材，四种元素，体，体，对吧？面，不好意思，你觉得木材像面？线。但是哪种结构上叫它长得像一条线，但是这条线还不懂是吧？所以看那个第一个，来铁不力学，木材，两元素也是一条线，那一根木板也可以当成梁。最后，到时候，借对，到时候我们基本上它没有什么结构墙，好，快速。那我们看一下今天，再看下一个例子，我们看刚才那三只小猪。 拆过70块，或者踩过70块，不拆，那你有没有拆？OK， 会拆过？没有，来前面有啊
面，
你的面是什么元素？你们以前学的这个杆啊、梁啊、立体的，应该没有说到去。那你这个面是什么？跟谁比较接近？跟杆比较接近，还是跟梁比较接近？
可元素
啊？
可元素
什么跟谁比较接近？杆梁。它是面，但是它的物性，它跟这张比较接近，还是跟这个粉笔比较接近？啊，粉笔，你说粉笔，你确定？压力一来，
哦，它是跟面比较
啊，然后这个面叫侧向角，啊。这像叫咩？那它立体 ，OK， 叫翘 ，OK， 翘元素。所以你的可乐瓶，就是你那架飞机 ，OK。然后那个那架飞机为什么？你的飞机为什么是那个可乐瓶？为什么有这个名？刚才是讲面的，那我们讲面的时候，从这个可乐瓶跟你的飞机很相似，为什么 ？Yes, okay. So the question here is, okay, what is the similarity between the can of soft drink and the aircraft structure? Yeah, they both have the skin, which are the cell structure. Okay, and then next is about the loading condition. What's the similarity between the can of soft drink and the fuselage of the aircraft? Yeah. Indeed, every time when you fly to the high sky, your aircraft is inflated. Exactly like the tire you have. You know your bicycle tire? You inflate it. Except bicycle tire is always under the inflation. But an aircraft structure is going up high, they have to be inflated to the atmospheric pressure so that the passenger will not explode. Okay? So that's why you can say a can of soft drink, okay, which is pressurized with the CO2. Okay. Likewise, in the aircraft structure, it's also inflated. It's inflated by the air. Okay, so that it can breathe at a good concentration. Okay. In this example, we're going to tell you that in the case of structure analysis, the scheme of the aircraft is exactly like the scheme of the soft drink can. Okay, they are membrane, but they behave like shells, so that they can sustain the internal pressure. Okay, but to make sure that the skin will explode, okay, what do you have? You need the rings. Okay, this is the same ring as you can find in aircraft and the soft drink can. And indeed, the ring, okay, is an invention by French. Okay, this is called Barquet. Okay, yeah. So this is the monocoque fuselage construction, which is very light. Okay, but strong enough against the resistance pressure. Okay, likewise. So next, in the beam element, you also can find that some are analyzed as the solid structures. Okay. Some are analyzed as the beam structure. When you analyze, which part of the structure are the beam? Okay, it's the part which is spanning between left and right. Given the same structure here, okay, the structure along the vertical line is what we call column, okay, and then the structure that is spanning across is called a beam. So if you are looking a chop here, okay, it is the same chop, but if you're supporting this against the weight, okay, I look at the paper, okay, but if I'm pressing this chop with the weight of the head, you can see this is under deformation. This is the same chop, same piece of solid, but in this case, this is called a rock element. But if I now put the chop in the horizontal or level span, if I load it at the middle, yeah, this is called a beam. Okay, you can see that. Okay, the beam made of chalk is very weak because the bitterness. On the other hand, if I use the chalk vertically, okay, but if I hold it and jump, okay, the chalk are not breaking. So this is the nature of the brittle concrete. Okay, concrete is quite solid. Okay, but it is brittle. Okay, so in this case, it is the same structure element. Okay, so in the early days, when you want to do the structural analysis, engineers will ask you, what kind of element do you want this to be? Okay, you have to choose between a rod, you have to choose between the beam. Okay, but ever since today, if you go and check an exit, okay, the element type they use is going to be a general type. They just assume this is a combination of the rock element and the beam element, and they call it the frame element. The frame element is going to be general, universal. Okay, you can subject it to any kind of loading, and they will give you the right value. But one of the problems is still there. Frame element cannot analyze twisting. Okay, you see the chop here, when the twist, okay, they will undergo the shear fracture. Okay, so yeah, in the case that if you're sure that there are no pure shear or pure torsion happen, then you can simply use the frame element. Okay. And lastly, okay, let's see. So in the end, you're going to be able to analyze multiple fields. Okay. Besides the static structural analysis, okay, you can add on to analyze the dynamic questions. So these dynamic questions, okay, you try to understand and solve it from the viewpoint of mechanics. What is static? Static is basically force connection is equal to N when A equal to 0. Okay, and what is dynamic? Okay, it's basically force connection equal to NA. Okay, but in this case, you are not analyzing a single element, you are analyzing an assembly of multiple elements. Okay, so we're not going to cover heat transfer. Okay, but it can be extended when you are using this as a field. So this is the analysis I mentioned. So for this part of the lecture, we're going to focus on linear static deformation. And the element we're going to analyze are trusses, pipe, okay, beam, with plane stress and plane strain element. Yeah, the same method might be extended to flag and shell or brick element. But due to the limitation of the tank, this part will not be tested. But in the industry, people are using solid element quite extensively. Okay. So let's come back to the structural analysis. Okay. Structural analysis yeah, come from two persons. Yeah. The Hooke's law coming from Hooke, and then the Newton law coming from Newton. Okay. But for our today analysis, we focus on the structure static analysis rather than the dynamic one. Okay. Okay. Before I have a break, then we'll come to the first step of writing our first finite element. What is the first finite element? As I mentioned to you, it is about this spring. Okay. When you do the pulling of the spring by your two hands, okay, how much force do you feel? Okay. So how to describe this deformation? This is the first thing we got to do, because we're going to write a general form of the Hooke's law. Okay, you can pass this around and pass the class to pull it. How do you write the Hooke's law? Okay. So you have the sensor in your hand. Your two hands, you are doing the pull of the spring. How do we analyze it? Okay. So we now, even though it is about element, but we now are going to analyze it by our support. Okay. If you have a spring, how do you define a spring? Your spring has 2 points. On the left point, okay, let's say node 1. Okay, you define the node. On the right hand side, the node 2. Okay? When you are pulling the spring, you feel the force. What is the force on the right hand side? It is F2. What is the force on the left hand side? It is F1. Okay? But we are going to teach computer how to do structure analysis. What do? You define force in the same direction. Okay? So this is my F1, F2. When you're doing the pull of the string or of the spring, how much is the deformation? You have the U1, U2. Okay? Can you now write Hooke's law? Okay? When with respect to the node. Okay? Not once and not two. Okay? So this is the first step. Okay, if I take you some method, let's see. Your first C programming. Okay. Okay, but in this case, our analysis is all view at the node. Okay, what's the force acting on the node? 1. Okay, you're going to have the force F1. Correct. So what is the force on the right hand side? Use your base. Your left node is moving to the right. Your external force, I presume it to be toward the right as well. But of course, I can say this is -1 to signify it is opposite. So what is the force on the right hand side here? What's the force here? what's the magnitude of the force? So this is the force coming from 大家知道So this goes to the spring force. So how do you apply the Hooke's law to find out the magnitude of the spring force? So the example of the spring you have already do the proof. How much is the spring force? If this point is moving rightward, what is the spring force? If you move right, the spring force is toward the left. But what's the magnitude of the spring force? Guy on the back. Okay, my two knots, they are linked by the spring. But how much is the spring force acting on the left node? Kami 多少？左手拉长这里，感受一下。How much the force you feel on the right hand？ 左边，左边，on the left hand。来，那个拿看好了再给他，再给前面就会看。Your right hand is moving. Okay, let's see here. This one is right foot. Okay, left hand, right foot. Right hand also right foot. Left hand moved by U1. Right hand moved by U2. How much is the spring force? 那你站起来拉一拉，这个参与系数是哪里？U1 right? Okay, yeah, this gentleman is telling us the spring force is U1 minus U2. And how about the magnitude? How about direction? Yeah, it's right. Yeah. For the first equation, you are right. Okay, now we apply the Newton's first law on knot 1. You are writing this equation. All the external force is written here. F1 minus K U1 minus U2. Okay, this is on the knot 1. Okay, first knot. Okay, and then next, we're talking about the second knot. Okay, you can pass on. So where the spring now? Then the guy who has the spring. Tell me what's the force acting on the right node? Okay, 你右手边的节点 ，V 是 U2，Y 是 F2。So what's the direction of the spring force? 这题是简单，给你先答。So what is the direction of the spring force acting on the top two? 那只有左右，不会有上下。Only left right, no up down. 那左右差一个，应该有机会。The right node moving rightward. What is the direction of the spring force? 右手向右。哎，你站。右手向右。那你觉得右手受到的弹力是左是右 ？If right hand extend right, what is the force direction coming from your muscle or tendon.
Okay.
Good. Okay, this is spring force. Then next, with the spring up. So how much is the spring force on the right hand side? So what is the magnitude of the spring force? The spring force. You calculate spring force by whose law? U2 减 U1. Okay. So this gentleman say the spring force is U2 minus U1. Okay, one important thing, when you are writing the equation, you are always cell-centric. Okay, you see, you write U2 minus U1 because you are moving with displacement U2. Just now, we tell you the spring force is also opposing. Okay, but you must cell-centric. You said the spring force is U1 minus U2. Okay, that's the correct step. Okay. OK， 所以你在一起有弹力的时候，一分辨方向，二看好你站在哪里，就用你站出的坐标。When you are writing the spring force expressions, first decide where is the spring resistance direction, and then second, express the spring force in terms of your standing coordinate. If you are standing on not 2, it must be KU2, okay, minus leveling point. If you are standing at not 1, you're writing KU1 minus U2, okay? Because you are assuming you are the most important. When you stand, move relative to the surrounding, okay? If you take that assumption, you are for sure right. But you also have to bear in mind, okay, when you move forward against other spring, okay, against the neighboring things, okay, you will face the resistance which is opposite to your movement. So this is the first point. Okay, with this in mind, now I can write my equation for not 2. Okay, look at here. What are the forces there? To be honest, you have very little forces, which is external force F2 minus the spring force. Okay, so this is the first equation and the second equation. And then, now we're going to do the solution. Okay? So the formulation is there, but now we are writing them in the matrix form. Okay? So which are the unknown? Okay, we write them very simple. Okay? We're going to write them in 2 ways, depending how you formulate it. You can write them in terms of displacement equal to the force vector. So this is the stiffness matrix. This is your displacement vector. And right hand side is your force vector. We want to highlight that the right hand side is your external force vector. So means I'm going to rewrite my expression. How am I going to rewrite my expressions? Okay, I'll take this away. Okay, for those who do this first finite element, please go back and draw. You must draw the 3-point form. If you are not drawing, you will not have the feel how to write the right one. You now have A U1 minus U2 is equal to F1. If you move the equations in this way. Second, if you move this, K U2 minus U1 is going to be equal to F2. This is my equation 1 and equation 2. So my equation 1 can be obtained from the first line. Okay, how do you do the filling up of the matrix? The first row of this 2 by 2 matrix come from the first equation. You have the K U1. K times U1 minus K U2. This is minus K U2. Okay, and then next you are filling up the second equation. Okay, so this is K U2 positive. K U2 positive minus K U1. Okay, minus K U1 plus K U2 is equal to the false. You have to change the color so that you are clear what we are writing. Okay. So you might ask, sir, why you make the life so difficult? Okay, it's just a book's law. Okay. But to teach computer, you have to make it universal. This matrix is going to work for one free spring. Okay? This is a free spring. What is a free spring? Okay? The spring which has the knot free to move. Free to subject. Force 1, force 2. Okay? You can hitch them up to the next spring. Okay? If this is the K1, if this becomes K2, let's share the same note. Okay? Subjected to different forces. Yeah. If you have this kind of element, you can later do the assembly. Okay? So that's why we are saying that this is the general form. Okay? So the first task I'm going to do is I'm going to reduce the truss equation. Okay, this is my truss equation. I'm going to reduce my truss equations to a simple Hooke's law. Okay? So this is a free truss. Okay, how do you make the truss not free? Take for example, not 1, U1, not 2, U2. They are subjected to force 1 and subjected to force 2. How do you make them the one that you feel familiar? Kalau bạn yêu đeo với đầu vấn đề là in this case you have two simultaneous equations, but how can I reduce them into the Hooke's law? Force is equal to A U2 So how do you reduce it? Okay. So when we are talking about finite element, we always start with the free truss of free energy. Okay? But in the end, when you apply the loading, okay? Okay, tell me, what is my F1 here? If this 2 is equivalent. What is F2? This is the free truss. This is the anchor spring. You are now having to do the equivalent. What is F2 equal to? Yes, you are right. The question is next. What is the this one is question here. What is the F1 here? And how about you? What's the F1 here? Yes, I think it's quite good. You know this is reaction. Anything you don't know, just give it the unknown variable. So this one is minus R. Okay? And then now, what else you know about U2? U1. Okay, in the case of finite element, we are solving for the unknown are normal displacement. This is the primary one. Okay. The unknown can also be reaction. Okay. Tell me. Okay. Is U1 known or not known? What is U1? Yeah, it's right. Say that U1 is 0. And then how about U2? U2 cannot be 0. Okay, U2 is unknown. Okay. Okay, from this example, what's the important lesson you got? In order to turn a free element into the anchor one, okay? In the analysis, we have the truss equation, which is first assuming the free nodes. But in the example, you are talking about the anchor rod. Okay? On the side of the anchor, you have the displacement 0. You have the reaction force being unknown reaction. Okay? You can choose the direction, but usually you choose it with the understanding of mechanics. You know that this is going to oppose external force. You can choose that. Okay, even if you choose it wrongly, it doesn't matter. Your finite element will get you the correct one. The anchor side, there is a proper name in the finite element. It is called boundary condition. Okay. And next, if you care about deformation, we're going to find the deformation. Deformation is caused by the loading. What is your loading condition? Okay. So your loading condition is your right hand side. Okay. F2 is equal to P. What you can say, oh, so my left hand side is also my loading. But opposite. So the boundary is U2 unknown. This is the free one. Okay. So simple. This is a simple understanding. Okay. Free node. You have to reduce them by applying the boundary and loading condition. Okay. So let's come and doing the solving now. Okay. What's the free equation? Simplest matrix K minus K minus KK. This is a square matrix times displacement U1 U2. How do you do the solving? Okay. Let's see the solved solution. Okay, to do the solution, very simple. Write down what you know about the boundary. U1 is fixed, so it is 0. And then write about your loading condition. You apply the non-loading condition. This is equal to P. This is equal to negative R. Okay? How do you do the solution? Okay? You do it very simple. Look at the matrix. Okay? Where is the free node? The only unknown is U2. This is the unknown. You take the row of unknown, okay, minus K times U1 equal to 0 plus KU2 is equal to, U2, okay, this is my P, F2 is P. Okay. So a quick check. Every time when you see an anchor, there must be a reaction which is unknown. Okay. So in this case, by looking equation 2, your right hand side is equal to P. So in the end, you find U2 is equal to P over K. Okay. So this is how you do the first finite element model. Okay. So this is the first step. You have to change your way of thinking. Okay. You have to think that you are a computer. You only do the standard procedure. What's the standard procedure? Read out the free truss equation. This is the one. Define what is the boundary condition. Left node is anchor, right node is free. Anchor 1 has 0 displacement. Okay. And then next, define the loading condition. Okay. Okay, do you get it? And then next, we might want to change a bit so that you don't just get the simple result. Let's say your right hand side is moving by delta. How do you change? If this is not 0, the left hand side is moved by delta. Delta is a constraint. Okay. When we say constraint, it means that it's a non-displacement. If non-displacement is delta, non-displacement is not 0. So in the end, you're going to have K, you're going to have K delta. Yeah. K delta divided by K. Okay. So then your displacement is going to be P over K plus delta. Yeah. So this is the way how your examination is set. We are changing the boundary, okay, to see if we are able to do model solution. Okay? Yeah. So that's your first final element. Then we shall have a break. We'll come back at at 3 and we'll continue the rest of the lecture.